So welcome everyone. I'm Eleonora Crenna. I'm a postdoc at the Technology and Society Laboratory at IMPA in St. Gallen. And today, together with Heinz, that will introduce himself in a while, over the next hour, we will guide you through this session on secondary resources, lithium-ion batteries technology, impacts, and recycling. So maybe Heinz, you can say a few words before going through the presentations.
Yes, thank you also from my side for your presence in this interesting session and also for the presenters. My name is Heinz Boni. I'm head of the research group, Critical Materials and Resource Efficiency. It's in the same lab as Eleonora is working. And Lorena, who will present today, is also part of my group. So I'm looking forward to an interesting exchange in this emerging topic.
Okay, so maybe I can just say a few words before giving the floor to our speakers. So we will start the session with all the presentations, one after the other, and then we will leave space for questions at the end of the last presentation. So meanwhile, you can feel free to leave your questions in the Q&A chat, and then we can pick them up at the end for the discussion session. Just a note to the speakers, please do your best to stay in the 5 minutes of your presentation. So we can start with the first speaker. The first speaker is Carolina Paes. Carolina holds a master's degree from the University of Ghent, and now she works at Minbiro. I don't know the exact pronunciation, I'm sorry. And she has experience in both environmental and social LCA. So she will present us lithium and cobalt for batteries in electric vehicles in the EU, life cycle sustainability assessment approach within the context of a circular economy. Carolina, the floor is yours.
Thank you, Eleonora. Yes. Okay. Thank you. Yeah, so today we'll discuss with you guys the lithium and cobalt for batteries in electric vehicles in the European Union, a life cycle sustainability assessment within the context of a circular economy. That was the work we developed together with Sonia Valdivia and Bernard Mazan, and all the results were refined now with the company Minbiro. So yes, next slide, please. So the research questions that we aimed to answer with this thesis was related with the environmental risks associated with lithium and cobalt production, and also the social risks associated with the lithium-ion battery supply chain. And the method we used was environmental life cycle assessment for the first, and for the later social life cycle assessment. We used the eco-event database for the first and the social database for the second one. And all of that, we could implement a circular economy approach to see as a solution to mitigate those impacts. Next slide, please. Yes, to assess that, we had to choose a functional unit. It was a battery from a Tesla Model 3 because it's the most consumed electric vehicle in the European Union at the moment. So to do that, we evaluate the mass of lithium and cobalt in the battery. And we assess the geographical location of all raw materials and processed materials in this process. The cell and the pack manufacturing was chosen to be in California, the US, and the transport from Germany, that is the country that most consumed this vehicle. And the end of life, it was chosen to be in Europe if the proper second use was properly done, and the recycling as well. But we know that it's highly likely if we don't do the second use and the recycling, this can end up in a landfill. And the biggest landfill in the world considered is Ghana. So we choose that also as at the end of life in this thesis. Since the focus is mostly on cobalt and in lithium, we model this life cycle assessment considering the Democratic Republic of Congo and lithium in Chile in South America. You can go next, please. So just go directly to the results due to time constraint. I will focus on the global warming impact and also the water consumption. And as we can see here in this graph, for the global warming, cobalt has a bigger contribution compared to lithium. And that is because cobalt is usually associated as a byproduct of copper. So their impacts are connected. And for lithium, when we think about what is the biggest contributor for this global warming is the soda production. For water consumption, the same pattern repeats for lithium. The biggest contributor is the soda production due to lithium brine. And for cobalt is due to mining activities, gravel and sand quarry operations. can go for the next, please. Yes. So the results of social life cycle assessment is a little bit harder to measure in numbers. So we use the rating scale proposed by UNEP, and that is from this color scale here, with green representing low risk and the red representing very high risk. And all the risk categories evaluated was workers, local community, value chain actors, including consumers, society. And we evaluated child labors, fair salary, working hours, forced labors, and all of that following the ILO patterns, and also GRR reports, in social interviews made with local workers. And with that, we could reach the results that the social hotspots are mainly connected to the raw materials production and to the end of life if not properly recycled. So here we can see that the sensitive points for the value chain of lithium-ion batteries are connected mainly with the raw material extraction in DRC and in Chile, and in the end of life if they are not properly recycled. With that, we reached a result that a good option to solve this problem is a circular economy approach. Next slide, please. Next slide, please. Yes, so the conclusion that we had is that with environmental life cycle assessment shows a need to improve or find an alternative for the solder production that is the biggest contributor for global warming potential. And for cobalt was also related to mining activities, so a new way of recovering these materials through recycling. And also think about how social aspects are impacting this extraction in Chile and also in DRC, and the end of life in Ghana. And a circular economy approach could be a good solution to recover lithium and cobalt for electronic waste that are badly managed in Ghana and other countries nowadays. And also, of course, these results need to be incorporated to further research for life cycle management reasons, and also to improve corporate social responsibility efforts. And combined with life cycle costing would be something interesting for the companies, but was not the focus of this work because it was not planning to lower the cost of production, only assess environmental and social impact. That's all that I had for today, and thank you for your attention.
I think we come to the next presentation. Please, the next slide, please. This will be given by Johannes. Johannes will share his screen. Johannes is from Oeko-Institut in Germany. It's a private association working in environmental issues, also a lot in e-waste and lithium-ion batteries. A lot of reports are available from them also on the internet. So please, Johannes.
Thanks a lot. Today I would like to talk about recycling and policy for lithium-ion batteries, not about recycling technology, as I won't have the time, unfortunately. But looking at lithium-ion batteries in general, we can see that there is a massive growth expected, which is also connected to a major resource demand, mostly driven by electric vehicles. And recycling itself is crucial for resource recovery and also coping with the resulting battery waste stream. However, the cathode materials, so the battery chemistries in general, are very diverse. And at the moment, at least, the cobalt content in these cathodes determines the revenue of battery recycling, which means batteries without cobalt, like LFP, for example, lithium iron phosphate, do not have any real material value yet, which is high enough to actually cover the costs of recycling. In general, lithium is also not valuable enough to make an impact, and in most recycling processes, it is not even recovered at the moment. But what is the role of recycling connected to cobalt and also to nickel? So we have a largely growing market, and with long-lasting products like electric vehicles, it will take a large time to actually get any of the large volumes which are growing back, which means that also the resources flowing back will be low in the beginning and only rise over time. However, if we actually want to have a good recycling industry, we also need policy to support that. So the European Commission had the regulation for battery in last December. They proposed legislation, and there they had the labeling and the battery passport in there, which is especially for second life, as you need a lot of information about the battery to sell it again. They have increased collection rate targets for portable batteries. They want to increase the recycling efficiency, and not only the general recycling efficiency, but also the material-specific recovery targets, which is very important, especially for lithium. At the moment, as I said, it's not recovered at all. And furthermore, there are recycled content targets for new batteries, which means every battery which is placed on the market in the EU from a certain point has to have a certain recycled content if it contains one of these metals in their active materials. Furthermore, there are other proposals like the mandatory due diligence for cobalt, natural graphite, lithium, and nickel, and also the provision of a carbon footprint, including a maximum value or maximum threshold from a certain point on, which could also support recycling. So already coming to an end, these measures won't be sufficient to completely flatten the resource demand, as at the moment, recycling is crucial, but not sufficient. So mining will actually play a role for the foreseeable future, and the impact of resource supply by recycling will only grow over time. However, if you then compare electric vehicles with cars with internal combustion engines, you can say that crude oil itself cannot be recycled. So if you actually achieve a share of electric passenger cars of 100%, you reach the peak of raw material consumption in the sector. And from that on, recycling ratios of recycling will actually grow if the policies succeed. That's everything from my side. Thank you very much.
Thank you very much, Johannes. You were very fast, and I think it was a good presentation. I liked it. It was very to the point. It was 4 minutes and some seconds. It was the shortest one I heard until now. So congratulations for that, and to bring your message over in a very short time. Excellent. So we come to the next presentation. Please, the next slide from the moderator from Schatzad. I think it will be coming. Yes, please, the next one. Yes, you probably have to go through that. Yes. Okay, time will start, of course, only when you start. Now we have a presentation from Maria Franco, who is an associate professor in circular economy in Bern at the University of Applied Sciences, with which we also work together in the area of modeling future flows of batteries and also the costs. She will present the system dynamics model of the diffusion of first and second life photovoltaics and LIBs in a circular economy. So please, Maria, the floor is yours.
Thank you so much. I don't know if I can beat the 4 minutes and some seconds.
Don't worry, you can use 5 minutes and some seconds.
Okay, good. So we change the slides. Okay, so good afternoon, everyone. This is a presentation of a system dynamics model that has been developed or is under development under the Horizon 2020 project CQ-SOL. Maybe you can go to the next slide. I'll tell you a little bit more about CQ-SOL. This is it's a funded project that focuses on the technical and also business model viability of second life PV panels and second life lithium-ion batteries from electric vehicles that are repurposed as energy storage units for renewable energy. Yep. So the model scope. Yeah. Can you go back just a little second? Okay. Some of you might not know what system dynamics is. This is a computer-aided approach. It's a computer simulation approach that it's aimed at enhancing the understanding of complex feedback systems and also and mainly to support the policy formulation process. So there you see an example of a customer interface or a policymaking interface where you can have some levers to see what the impact of those levers would be in key selected output variables from the simulation model. And then we go to the next slide. The model scope, it covers the years from the year 2000 until the year 2050. It covers, as I said, strategies of new PV and LIBs for energy storage, and also second life PV and LIBs. And it has been developed for the base case of Germany, for the purposes of the consortium, of the CQSOL consortium, and also because of the country's large amount of data regarding PV, and also recently also on home storage systems. Next, please. Thank you. So this is just an overview of Germany's landscape in terms of PV and battery capacity. You see in both graphs how as the installed capacity, both for PV and the dark blue line, has been heavily increasing since the year 2000, also since the year 2015 for battery, for home battery systems. Also, that is reflected in the learning curves of the cost or the price for PV systems and also home storage systems. Next. This is an overview of the model boundary chart, what it includes. In the middle, you see the ESTA simulation model covering the residential, industrial, and utility subsectors. Then you see on the left-hand side the input parameters that we use, among them population growth, household size, also data about the electricity load profile for different consumer groups, also technical parameters for PV systems and also for battery systems. And then in the output parameters on the right-hand side, or what the model produces or gives as output, you also see the volumes available for reuse, both for PV and LIBs. And also, what's most important in this simulation is the diffusion among households of these different combinations of new and second life PV and batteries. And then we go to the next one, which I won't probably go through that. It's a little bit complicated, but that's a simplified, it's a simplified view of what the simulation cover. In the upper part, you can see some of the technical parameters of, for this case, the PV. And then you also see in the down part of the picture how mainly it's financial indicators or the levelized cost of electricity, what drives the agents in our model to move to the different combination options between new and second life. And then I will probably go to some of the conclusions. Yeah, so some of the preliminary insights of this model, as I said, it's still under development, especially for the battery part, regrettably. But some of the preliminary insights are that new PV installations of PV systems in Germany, in addition to motivations such as the personal contribution to the energy system transformation, are mainly driven by financial factors such as feed-in tariffs and also related profitability. A main key thing here is also what's been happening in Germany with rising electricity prices being right now the main driver for the market uptake of new PV and also battery systems for self-consumption. Also, another key important thing here is at the market level, or from the market perspective, the decrease in equipment prices, again, both for PV and LIBs. You saw that in the graph. And a key thing also in this point is that this decrease in equipment prices for both PV and LIBs are also leading to early replacement behavior. So more from the behavioral part of the customer. And these are things that are not right now taking into the statistics, only more technical parameters about early failures or late failures in lifetime, but not really how prices are going to lead to early replacement and therefore higher volumes of waste earlier than expected. Also, that the volume of available second life PV, as the simulation has shown us, is that it is highly dependent right now on several factors, all of them bearing a high degree of uncertainty. And those factors include growth rates of PV install capacity, how will they develop in the different countries, also data about failure rates.
Yeah, 6 minutes past.
Yep, sorry, I maybe finish here. Age cohorts only and repair types of used PV. That means which type of failed PV panels can be actually cost efficiently be repaired. And the same for LIBs. And I finished probably here, is that it's become evident that a measurable end-of-life criteria also both for PV and LIB must be there. For the case of batteries, the residual usable period and the resulting usable period for repurposing, in this case for second life, all of this to ensure safety and performance, that it can be maintained in reused batteries. And for this also battery passports, standardizations and certifications are needed. So thank you.
Okay, thank you very much, Maria. You passed the time slightly, but you see that we are tolerant, we are friendly with you, with all of you who still have to present. So
thank you so much.
So just we remind you when 6 minutes pass, I think then you're really over the time already, and of course it makes you nervous when you mention that. But yeah, we will measure the time also for the next presentation. So try to be short, bring it to the point. But thank you very much, Maria.
Yeah, so the next presentation is from Lorena. Lorena is a scientist at the Technology and Society Lab at EMPA, so she's a colleague of ours. And yeah, her work aims at improving the resource efficiency of recycling processes. So now the floor is yours, Lorena.
Good afternoon, everyone. I am Lorena Toledo, and I'm going to present the results of a project where EMPA supports the development of a recycling plant to treat lithium-ion batteries. First, a short overview about the context. This project is in collaboration with Keywords, a Swiss company which produces electric vehicles for industry, the private sector, the Swiss postal services, and even for sports. Now, what do these vehicles have in common? All of them, of course, have a battery, but more specific, a lithium-ion battery. But for this project, there is a more important characteristic, and it's that all of them use the same kind of battery, which is lithium iron phosphate, or LFP. Our project focuses on the recycling of those LFP batteries. But why? Currently in Switzerland, lithium-ion batteries are treated with pyrometallurgy. This technology is adequate to recover mercury, zinc, and ferromanganese from old batteries. But lithium-ion batteries have a problem because valuable materials are lost, and it's a technology which requires high energy consumption. So, based on these reasons, we identified a need for a better battery recycling process, and we also established priorities like fulfill all legal and safety requirements and develop a recycling plant with low carbon footprint. So let's see what were the ideas. Before recycling, when the lithium-ion battery reaches its end of life, a capacity test is performed to see if the battery can be used in a second life either in another vehicle or energy storage. If the remaining capacity is less than 50%, the battery goes to recycling. Let's open an LFP battery to identify the challenges for the recycling based on its components. The first one was how to open the batteries, semi-automatic or automatic process. The second one was we need to control the working atmosphere to guarantee safety and environmental protection. And third, separation of all the materials and analyze their quality to assess the efficiency of the process. So the recycling plant was divided in two phases. The first phase corresponds to a semi-automatic dismantling process, where the outputs are the housing, the plastic separator, and the electrodes with the coating materials. This phase is completed. The second phase is a water-based process where the cathode and anode are synced in a water bath, and the outputs are a clean aluminum and copper foils, lithium iron phosphate, and graphite. This phase is ongoing. In this video, you can see the results of the first part of the recycling plant. First, the batteries are discharged and introduced in a machine for the sewing of the housing. Then, with pressured air, they eject the electrode packages from the housing. And finally, in this glove box, there is the separation of the plastic separator the cathode and the anode. I'm going to close my presentation with the results of phase 2. In this video, you can see a demonstration of how the coating material, in this case lithium iron phosphate, is separated from the aluminum foil. Then the recycled material is analyzed with different kinds of techniques to evaluate the quality. Here you can see one of the results with a scanning electron microscope. This is how fresh material, lithium iron phosphate and graphite look, and then we compare with the structure of the recycled material. Finally, we are working to answer the following questions. Can we remove the impurities of the recycled materials and go back to the structure of the initial one? And is it feasible to obtain battery-grade material with low carbon footprint process? So, thank you very much for your attention. And do you have any question?
Thank you, Lorena. Presentation perfectly on time. So our next speaker, if we can go to his presentation, is Leopold Peiseler. Leopold is a PhD student at ETH in Zurich, here in Switzerland. And the goal of his research is to support policies along the supply chain of lithium-ion batteries to minimize their environmental impact. So Leopold, now the floor is yours.
Thank you very much. Just going to share my screen. Great. So once again, thank you very much, Eleonora, for this little introduction. Today, I want to talk about our ongoing research project about the identification and quantification of potential levels to reduce the carbon impact of lithium-ion batteries. So since you're already here, I presume that you yourself have a motivation why batteries and materials in batteries need to be sourced sustainably. But nonetheless, I would like to lay out our motivation for this research project. So I think we can agree that batteries are an essential enabler for the electrification transition, so abandoning the combustion of fossil fuel. This then opens the door for business opportunities with strong growth rates until 2030 and beyond. On the other hand, however, we do have to face that lithium-ion batteries have sustainability challenges ranging from the carbon footprint over to water user resource depletion. And on top of that, batteries are a complex technology. So there's a lot of tacit knowledge involved in the manufacturing and design of batteries. And this raises challenges to engineers. So our research question we try to answer here is how and to what extent can the life cycle carbon footprint of lithium-ion batteries be reduced? So we're not the first really to look at this. We started off with a literature review of life cycle assessment literature, or LCA. In general, LCAs are a powerful tool when measuring impact categories of sustainability for products or services. In the case of lithium-ion batteries, however, we have to face moderate data availability and significant methodologic inconsistencies between different LCA studies. So on the right-hand side here, you can see a little meta-study of existing LCA literature, which I conducted earlier this year. On the y-axis, you see the global warming potential per capacity. And not going into detail here, I would like to focus on the rightmost column, where we have 41 different LCA studies. And the point I would like to make here is that even amongst academic literature, we do have significant uncertainty in the carbon footprint of batteries. On top of that, literature that analyzes mitigation options usually considers those options in isolation and doesn't necessarily technically assess the feasibility of those. So this really makes a strong case for a technical model covering the entire life cycle and quantifying the greenhouse gas reduction potential of levers and also acknowledging their interdependencies. So to this end, we're currently working on a Python model, including an upstream modular supply chain, followed by a first application simulation where we use a degradation model for lithium-ion batteries, which then, if applicable, is also used to determine the second life application stage. and then you would get a carbon credit at the end for different recycling methods. And this model here really tries to give us an estimate on the carbon footprint of batteries used in different applications. So battery, personal battery electric vehicles over to different stationary applications across the entire life cycle. And we use this model, which we're still developing, to determine the impact of different mitigation levels. So for this, we first use or define our own supply chain, starting with the metal extraction over to refinery and the precursor production, continuing with the cell production and battery production. This then is followed by the use phase and, if applicable, the second life and end of life. Our next step then is to identify different mitigation groups and the associated levels. So in this case here, for example, let's take cell chemistry, modifying the cell chemistry. How would that change the carbon impact on the different life stages? What you see here are pie charts, and these are working hypotheses, so not results yet, but what we expect for changes to see. While we do see limited effects or moderate effects on the upstream supply chain, we do expect significant impact of the cell chemistry for the use phase due to different aging mechanisms for different cathode cell chemistries. And we did that for a couple of mitigation levels sorted in our mitigation groups. So far, what we can tell is that the cell manufacturing is an energy intensive process. So low carbon energy is really decisive here. This is not a novel insight, but just confirmed by our model. Next, engineers have to make trade-offs when designing batteries. So the module and battery design actually play a role, even for carbon footprints. And lastly, the fit between the battery chemistry, so the cathode chemistry and anode also, and the application type is actually very important to get the best fit. So there's not a one-fits-all solution. That's it from me at this point. Thank you very much for your attention. I'm looking forward to your question. Thank you.
Thank you, Leopold, for your very interesting presentation. So from the chat, I see that there's a question to Lorena. So the question is it necessary to treat only identical batteries? For instance, same brand, same chemistry, same shape? Or could this type of recycling solution be applied to a mix of different sort of batteries?
Like, this is the quality for this project that we started to analyze the recycling process based on the facility or the characteristic that we have just one kind of chemistry. So this allows us to easily separate the battery materials. Right now, it's not possible to do a mix, and we are analyzing on the next phase if it's possible to recycle NMC or other kind of batteries.
Okay, thank you very much for your answer. So at the moment, I don't see any other questions from the audience, but I might have a question for Carolina. So thank you, Carolina, for your presentation. And actually, it's just a curiosity question. So which other impact categories in the environmental life cycle assessment did you find relevant to explore beside the climate change and the water consumption? Carolina?
Yes, I'm here, sorry.
Yeah.
Sorry, can you repeat the question?
Yeah, sure. I mean, it's mostly a curiosity. So I've seen it in your presentation, you showed the results for climate change and water consumption. And I was just wondering if you found some other relevant impact categories in the environmental life cycle assessment that can be maybe interesting to explore in this context of mining for lithium and cobalt.
Yes, indeed. I evaluate around 7 impact categories, but I only present those 2, otherwise the time will be overcome. But besides like land use, water use, and ecotoxicity, and eutrophication, fresh water, and fossil fuel as well. I try to apply all the impact categories that are most common to mining LCA. So I follow the environment footprint methodology to do so.
Okay, thank you.
Sorry for the delay.
No problem. Heinz, do you have any question?
Yes, I have a question to Johannes. You mentioned in one of your slides that there should be measures taken to flatten the resource demand for batteries. What do you have in mind? If you have said this without commenting it a lot, maybe you can say a bit more about that.
Yes, actually, I had a slide about that, but then I left it out due to time reasons. So there are of course, there are a lot of other measures to flatten the resource demand apart from recycling, which is like sufficiency. So just less individual transport with your own car, which means you could do car sharing, or you could go by foot, by bike, or public transport. You could actually substitute certain minerals which are critical, like cobalt. When you have cobalt-free cells, like LFP, you can increase the material efficiency and the innovation by innovation. So if you have, for example, just less inactive materials because you have a higher energy content in your cell per active mass and volume, and yeah, all these can lead to less resource demand, but at the end, yeah, we still, at least for lithium-ion batteries, we still will need a lot of resources.
Thank you for that answer. You would have had 53 seconds left in your presentation for showing this slide. So.
Yeah, I think I was faster this time than during practice. So.
Okay, I think there's a question coming in from, at least in the chat in the Zoom. I have a question. Let me see. From Leopold. You have questions to the other presenters?
Yes,
maybe
cool.
You can, yeah.
Thank you, Hans, very much. So yeah, first maybe to Lorena, one question about your last slide. It was interesting to see the comparison between virgin material and material you recovered during your recycling process. And I was just wondering, how, like, could you maybe add a few words to like how feasible you think it is to get out the binder and carbon black to get closer to the virgin material?
For this case, is feasible because the binder is a water-based binder. So that's why we can actually separate pretty good with the water-based process. And then in the phase that we are right now, we want to have two options. That is a thermal treatment, and the other one is a leaching process. We are trying to check also bio-leaching to remove the impurities and to go back to the first structure and to see if we can apply this material to other possibilities, or we can get battery grade. But this is ongoing research. I hope I answered your question.
Thank you. Lorena, you said you have more questions, but I think I would like to also give the others a chance for a question. I see here that Markus Spitzbart, our colleague, with whom we work together in an international project in Ghana, he is asking, will it be possible in the future to recycle lithium batteries with revenues, or will there always be required a gate fee? This question goes to all of the presenters. So maybe somebody wants to take it up, maybe Maria. You have modeled this economic part of the whole supply chain, reverse supply chain. How do you see that in the future? Is it possible to finance it just by the income of the material, or you think it will be a gate fee will be needed?
Yeah, so from our perspective, also for the PV part, it's a question about also the volume that can be taken back. You know, also for the case of PV, that's a key thing. And another competing market factor is the decreasing prices, as I mentioned, and whether from the I'm talking more from the customer perspective, from the buyer perspective, whether it actually makes sense to do second life use for PV and battery, and for which cases. In the case of CQ, so for instance, for the case of PV panels, when you buy or when you get a panel that has been decommissioned because of weather extremities or some sort of failure, and you get that panel that is 5, 6, or 10 years old, there is some power degradation already in the panel. It doesn't perform the way it should perform, and then space requirements are different than with new, more efficient panels. So it's not for every use case that this business case of secondary use or reuse or second life use will be given. We are trying to investigate for which specific market segments or for which specific customers this sort of reuse case will be feasible.
Thank you very much. Very
Can I
comprehensive and good answer. I also thought that Johannes might say something to that question.
Yes, we talked to a lot of recyclers, and as I said in the beginning of my presentation, it depends highly on the cobalt content. If you have lithium cobalt oxide cathodes in your material, which is common in mobile phones, in general, small portable devices, you will have a positive gate fee. So you will get money for the battery if you get it in front of the recycler's recycling plant. I mean, logistics is another topic, but if you get it in front of the recycler, then you will get a gate fee. However, if you do not have any cobalt in there, or if you have an NMC battery with a high nickel content, it needs a very large scale to actually come to zero. At the moment, I think due to lower prices, you also have to pay a little bit. But in the future, if you have a large scale, it could be possible that you also get a positive gate fee there. And at least in Asia at the moment, you will have a positive gate fee, but it also depends highly on the possibility of disassembly, if it's easy to disassemble, and also if the content of your material is known. Of course, there's always the possibility of refinancing due to partly second use, but this is only possible if you actually have low labor costs. So if you're in Nigeria or in Ghana, you can disassemble batteries and try to sell the good batteries, and the rest this can finance the recycling. But for batteries with no cobalt content, it will be very hard. I mean, there are a few recyclers which say that they could do this in the future, but it depends highly on the prices of resources, and so it's hard to say if there will be positive value for that.
Okay, thank you. I thought that James Souder has addressed the question to Leopold. I've not, and maybe Leopold, you can see in the chat the question and give an answer right away or then in written. I don't know if Eleonora has questions or somebody else.
No, actually, I would address this last question for Leopold, and then we can share the screen for the voting session.
Yes, okay.
Because we are reaching the end of the session.
Ah, yes, I see. Time is running. Yes, please, Leopold.
I'm a bit confused. What question I'm supposed to answer?
The question which is now in the
right.
chat of the Zoom link also, and also the other chat too.
So
about the CO2 credit for recycling.
Exactly. So the question from James that says, what are some of the challenges you're facing when determining the CO2 credit for recycling batteries across the different recovery methods?
Okay, yeah. So thanks for the question. First of all, you always substitute something. So first you have to determine what's the carbon footprint of the material you're going to try to substitute in the first place. And there's already your first barrier, because there's not one right answer. So you have different sources for one metal, and it already depends on which kind of metal or which kind of source you take. So that's the first barrier. Then moving towards the actual recycling process, there's a trade-off on how much energy and process emissions you put into the actual recycling process. So at the end, what you're looking at is how much energy am I using to recycle, say, 1 kilogram of lithium. And then the next step is also what grade is your metal then? So is it reusable? So that's sort of like to the question which I addressed to Lorena. Just because you get the metal out of your battery doesn't mean that you can reuse it directly. So you may need some extra steps in order to purify or like change the material properties of what you get out. So those are like on a very high level the issues or challenges you have to face when modeling this.
Perfect. Thank you very much, Leopold, for your answer. So still 1 minute before closing this session. I just want to take this time to thank all the speakers. Your presentations were really interesting, and thank you for sharing with us your knowledge. And yeah, I think it's
same from my side. Very interesting presentations. I think it was really, they fit together very well. I think it was really turning around the same issue from different perspectives, and that was the idea of such a session. I liked it very much. Thank you very much also from my side.